Hi class, this is our lecture number 10, naive Bayes and maximum a posteriori estimation. We'll focus some on each because you need to understand, we need one to understand another. Outline is map estimation, maximum a posteriori estimation, and the naive Bayes classifier. Let's see how that goes. Let's start with the map estimation. So let's say you suspect the coin is biased, then what do you do? Do you still use maximum likelihood as before? Will it give you the correct estimate? Probably it will if you throw the coin enough times, right? Because it does converge to the true mean. But what if you only get to see a few throws of the coin, and what can you do then? Yes, can you use the knowledge in this estimation? Can you use the knowledge that you already have? That is the question. In maximum a posteriori, everything was determined by the data. Your data would give you an estimate of the parameters or the amount of data. And as we estimated sample complexity, if you want to be within certain levels of confidence, then you need to collect certain number of samples in order to be within that level of confidence. That may not be always possible, that may not be always desirable. So if we have some prior knowledge, we can minimize that, right? What if we know something already? Can we weave in that knowledge into the process, into the estimation process? So for example, we know that the coin is close to 50-50. What can we do now? So this kind of notion of being close to or being uncertain is the whole crux of Bayesian approach. In the Bayesian view of the world, we don't know anything with certainty, and so we must quantify that uncertainty of our knowledge or uncertainty about every parameter probabilistically. So if we know or if we suspect that the coin is close to 50-50, how can we express this suspicion or belief, our prior belief? And Bayesianists suggest that it's best to use probability as the logic of science and base everything on that. So let's follow the Bayesian way. Follow the Bayesian way. Rather than estimating a single theta or a vector of all parameters of our distribution or likelihood, we will obtain a distribution over possible values of theta. So theta is parameter for our likelihood here. Well, this is actually posterior, but theta is parameter for our likelihood that is not on the board. I will put it on the board for you. So our likelihood given the parameter for this family of distributions, so fixing a distribution, what is the probability of observing that data? That's our likelihood. So, and theta is a parameter here. When we talk about 50-50 split, or theta for the coin is 1/2, for the flip coin, I said theta is a vector. In our case that we're considering now as an example, theta is just a scalar value. And if we are Bayesian, and if we are also reasonable about uncertainties in life, we would not say that our probability of theta being 1/2 is 1, right? We maybe would say, well, I'm pretty sure it's 1/2 of 50-50 chance for heads or tails, but have some uncertainty and it could be a little lower, a little higher, or maybe you've seen how this coin was just minted and it's just fresh from the start and the balance is pristine, so you are more precise and more sure about what's going on. But still, you leave some uncertainty about this value because we're in real life and anything could happen and you're not absolutely sure in anything and it's all fuzzy and warm. But then when we do an estimation of posterior, so remember, we do want to know the value of theta. And this is our prior expectation of what this parameter is before seeing any data. Remember the fish example with salmon and sea bass. But for posterior, the distribution could change because our data will modify our prior beliefs according to the actual process in the world that is happening, according to the actual true probability or true value of theta. Well, and again, a Bayesian, a hardcore Bayesian would probably say that only distributions are true and there are no actual values and it's all fuzzy all the way down there. So prior distribution, what kind of prior distribution do we want to use? Think about it, how to come up with one. So philosophical approach to this says, well, we want a prior distribution that represents expert knowledge. So we want to be able to represent a knowledge of an expert or our own knowledge in this case in the form of probability density. And that's a philosophical approach. That's probably when we will get the best results too. Another approach is engineering or pragmatic approach. We want to pick a prior such that the form, the shape of our posterior is simple to deal with and that we can work with. And one of such priors, well, one of conditions would be, well, can we pick a prior that when we know nothing, can we quantify that? Can we encode that? So there's few conditions. One is we want simple posterior form, and we want to follow engineering approach when we can, just to simplify our lives. Or if philosophical approach simplifies our lives, we can start with philosophical approach, the philosophy of pragmatism. But that's just the first condition here. But another one interesting is what if we know nothing and then we want to pick an informative prior? So for theta, in our case, we're lucky because we can pick an informative prior that is a proper prior, proper density, probability density that integrates to one and everything. Yeah, so this is a uniform prior. Basically, we're saying, okay, I don't want to assume, I just want to encode my knowledge of lack of it as a prior distribution. But few interesting things connected to the uninformative priors. So often we can write down probability distribution of data with some parameter lambda, and then we want to say, oh, why don't I just take this parameter lambda and just set probability of this parameter like uninformative 1 over lambda everywhere or something like that, or one over the range, but some of the, like sometimes the ranges of those parameters are infinite, and like lambda could be anything, and your probability distribution would integrate to infinity. It wouldn't integrate to one if you just simply set this value as uniform, or the same everywhere. So those priors were so when you use a non-uniform prior that doesn't integrate to one, or cannot in principle be normalized to integrate to one, um, can you use it? And turns out you can if the resulting posterior is proper distribution, normalizable, and those things can happen. And in this case, this prior is called improper, and people do use those improper, non-informative uniform priors, or uninformative. So, but to get the simple posterior form to follow through with our engineering approach, we usually talk about and use something called conjugate priors. In this case, by carefully picking a conjugate prior, we guarantee that we will get a closed form representation of the posterior. So we will get probability, again, posterior probability of our theta given data. We have the data. What is the most, what's the probability of a given theta given that data, right? And we maximize that, that's the posteriori. And this distribution will be in closed form if we choose an appropriate conjugate prior. And conjugate, it means that, again, in the Bayesian theorem or Bayesian formula, means that the posterior will have the same form as the prior. So the same functional form at least. And everything back to and thanks to Thomas Bayes, who published in 1763 an essay towards solving a problem in the doctrine of chances in philosophical transactions of the Royal Society of London. Well, what he actually discovered was conditional distribution, but from that, of course, the Bayes rule follows. And chain rule of probabilities, or Bayes rule, they're related. So the chain rule says if we have a joint distribution P of xy, we can decompose it as a product of conditional and product of marginal. And if you visualize my explanation of where does the Bayesian theorem comes from, you will see that this quickly follows through because our conditional is nothing but normalized by the marginal. Okay. I hope it's clear. I hope you can go the other way around. Another thing that I would like you to be clear about when you deal with this is that this sort of cross section of chain rule can be done indefinitely. You can condition on Z, shall we do this? No, let's do this instead. You can condition on y and z and get a joint of y and z. But wait a second, this itself can be conditioned on z and prior on z. Right? So we can keep decomposing our distribution by multiple ways, conditioning on one variable or another. But yeah, like basically what I wrote was this. Okay, you must follow, don't fall asleep. Do this on a piece of paper. So I legitimately wrote this, right? Because I can do that. I am sort of dividing by x and z. Oh, see, I'm mistake. I'm dividing by y and z joint in here. But then I can further decompose the joint into project of marginal and the conditional. And I can do that multiple ways. I can condition on x, I can condition on y, on z, multiple other combinations. So, and once this product is computed, well, we get the joint. So that's one thing. But then from this too, we construct the base rule. That's simple, right? So divide by py, both parts, you'll get this here and this here. Base rule is important for reverse conditioning property, right? So if we know how to condition on x in this two variable case, then we can apply Bayes rule and reverse condition on y, figure out what is the functional form or what is this condition on y distribution looks like. Okay, let's talk about Bayesian learning now. So when we do Bayesian learning, instead of our maximum likelihood estimation, we have our data still. D is our data as before, right? And remember, D is a set of our samples. And samples, and each sample is either a head or a tail. It's going really slow, so you're not confused or puzzled on what's going on. And this is probability of our data integrate over all possible data outcomes. Uh, because we want to maximize, eventually we want to maximize our posterior, we actually don't care about the normalization factor because you're dividing everything by the same number and the maximum location of the maximum. This theta max doesn't change. It's the same. So we usually, to simplify matters, prefer to work with um, just the proportionality likelihood times the prior. And we know that it's likelihood times the prior, or what I just said. Okay, now what are the differences of maximum likelihood estimation, which you all now perfectly understand inside out from the last lecture? And what are the differences of MLE and maximum a posteriori estimate? So MLE, of course, you know all of it, nailed it, is choose the value that maximizes probability of observed data. So our maximum likelihood estimator is argmax of the likelihood. That's why we went through the trouble of differentiating the likelihood and equating our gradient or our gradient of the likelihood to 0 and finding the solution that uh, maximizes the likelihood. So maximum a posteriori or MAP estimation works the following way. Choose the value that is most probable given observed data and prior belief. So um, yeah, so observed data is here. And what is the most probable data given, what is the most probable value of theta conditioned on this data? The data is fixed. What can we do? But since posterior is proportional to likelihood times the prior, with introduction of the prior, we will be able on getting pragmatically useful values of our estimate for theta, even when we don't have enough data to estimate precisely with the accuracy and precision needed for MLE estimate. That's helpful also to think about when MLE and maximum a posteriori are equal. When are they the same? So when are they the same? Think about it. Well, now you see everything in front of your eyes. MLE and MAP. Or usually, and what we should do, we should maximize log likelihood rather, right? Because our probability of data is a product. So we have a sum of log of individual data set. Yes, the infamous IID assumption. So that's MLE, maximum likelihood estimate. Maximum log likelihood. Yeah, thanks for paying attention. We can do the same trick here again, and what do we get? We get log px by theta plus theta. Argmax. So when this equals to that, precisely in the case when this is constant. For uninformative priors, uniform priors, when probability of any theta is the same as any other theta, this is a constant in our maximization, and we will still select the same theta as maximum likelihood. Easier, right? So now we know that we're pretty close. What do we have? We now want to try and actually do it, actually solve our problem. Uh, remember what we started with? We started with the coin toss. And the coin toss maximum likelihood estimation gave us exactly what they taught us in school or in probability 101 classes, compute the frequency of the heads. And now you know why. But what if we have some prior distribution about what is the frequency of the heads, or what is the probability of the coin falling heads? Let's try what we do in this case. So we will consider our prior or our likelihood. We model it as a binomial likelihood, and binomial likelihood is as before. Uh, this is the probability of the coin falling heads and the number of times it fell heads in this series, in this data set, and then the number of times it fell tails. And of course, the probability of tails is 1 minus probability of heads. And then we'll just look at all possible ways in this particular series of coin tosses this outcome is possible. So like we have all possible outcomes and we have one observed outcome. And how likely is that outcome among all possible outcomes is modeled by this expression. So this is a likelihood, binomial likelihood. If we choose the prior as beta distribution, or we will choose beta distribution as our prior, then the following magic happens. So first of all, what is beta distribution and what is prior? In every prior is defined on the range that the parameter is taking. So our theta can be anything from 0 to 1. Well, 0 and 1 would be highly unlikely, but I guess possible, right? So this is our theta. It can take any parameter, any value between 0 and 1. And beta distribution models exactly this situation where yeah, I should have theta here. Okay, the beta distribution is defined on theta, exactly on the parameters. Every prior distribution on the parameters is defined on the range of those parameters. Uh, yeah, coincidentally, the beta distribution looks similarly to the binomial. But what's more interesting is that although it is parameterized by two parameters, beta heads and beta tails, it is quantifying or encoding our belief or our uncertainty about the parameter itself, not about the probabilities of our data set and things like that. So normalization factor, everything's normal. So look what happens if we use beta distribution as our prior on theta. That is, we compute posterior as this product where this is beta and posterior likelihood, sorry, is binomial. What will the posterior look like? Well, the posterior is also beta distribution. Yes, as I said, posterior is beta distribution. And maximum a posteriori for binomial distribution will look as follows. So we have binomial likelihood on the left right here. And we have beta prior on the theta, on the parameter. And then if you multiply them through, you will see that you'll get beta posterior distribution. So as expected, we picked the prior exactly with this intention pragmatically to have the posterior to be of a manageable form. And the interesting part to note is that after you can do that as a homework after the actual multiplication of multiplying through, you'll see that the beta parameters become your parameters encoding your prior beliefs plus the actual measurement, what's in the data, how many heads, how many tails. And this is your belief of frequency of heads and frequency of tails, sort of that could be interpreted like that. And since our prior and posterior have the same form, it's just a demonstration or a proof that it's conjugate prior. And in this case, maximum a posteriori distribution becomes the following. You can also verify that for yourself, but we'll see now it's not anymore as MLE, it's not anymore frequency of heads. As you notice, your prior information plays the role. Prior beliefs or prior knowledge, expert knowledge, and expert information plays a role. So let's look at how beta distribution looks like. So beta distribution, those are different examples. As before, it's defined on the range of from 0 to 1. This is your theta, and this is how you expect which value of theta is more likely for alpha and beta parameters. Kind of abusing the notation, right? On the previous slide, we call them beta heads and beta tails. It's the same as alpha and beta here, easy to follow. So the lower they are, the less concentrated the distribution is. The higher those parameters alpha and beta are, the more concentrated distribution becomes the distribution over prior. So beta conjugate prior, again, let's look at our posterior, which is beta distribution now. And look what happens with this distribution as we sample more data. So when we start and we say our belief is that the coin is fair, we put beta heads and beta tails equal 2, and that's what we get. That's our prior distribution. 1/2 is what we expect for the parameter theta to be. But then we start sampling, and beta h and beta t stay the same. They're still 2, but as we keep throwing more tosses, as the number of tosses increases, we get more concentrated distribution. And basically look here, when alpha h and alpha t are large, this tiny values 2 and 2, imagine we've done 300 tosses, 300 throws, and we got 120, I don't know, and 180 for heads and tails. 122 versus 120, when you have 180 and 182, it doesn't much matter anymore. The more data we have, the less our prior matters, and we kind of leaving an opportunity for learning. Yes, we had some knowledge, we encoded it in our prior, but then we're learning through the new data and we're changing our beliefs. This is called Bayesian learning, and basically the prior effect of prior washes out. So it helps to regularize the problem. Well, one side note, side comment: when your prior is improper and you have no data, then of course your posterior will not be proper either. It won't work. But once you start having some data, even with an improper prior, you can correct and get a proper posterior as a distribution, which is a nice property of Bayesian learning. So for small data, you can correct the lack of the data with your assumptions and still be able to act and make decisions if we are encoding a robot uh, into the process. But for large data sets, you are kind of liberated from the fear of being wrong because you made wrong initial assumptions, because the data will help you to change your ways. Another distribution of a similar sort is multinomial distribution. Instead of flipping just one coin, what if we are throwing a die? What distribution will be there for the categorical variable with 6 outcomes? And this is the multinomial distribution. So let's denote our likelihood as multinomial. It's a parameter per outcome, power, the number of times this outcome appeared in the series of tosses. So this is our multinomial distribution. So now we want to find a map estimate of those parameters. Which distribution shall we pick so that it's easier to deal with, and what will it look like? And if we pick Dirichlet distribution as our prior, which again is a product of those parameters power beta I minus 1, appropriately normalized. And if we do that, then our posterior is also a Dirichlet distribution with this nice convenient property of our prior belief of the number of outcomes of this category and our actual measurement. So a similar effect will happen here, will come through that the more data you have, the less your prior will matter. If your prior was correct from the get-go, then you're only reinforcing your belief. But if it was wrong, it will eventually wash out. And so just an example of what this Dirichlet prior is, it's again defined on the space of parameters. So imagine what is a Dirichlet prior for two variables. Dirichlet prior basically is a distribution defined on this line because you want your theta 1 and theta 2 to sum to 1. So you want all of those distributions, all of these parameters to sum to 1, right? You want probability of those categories to sum to 1, and the distribution will be defined on this line. In this three-dimensional case, it will be defined on the simplex. So you have x and y and z, and you want their sum to be equals to 1, and that defines a simplex. Basically, Dirichlet distribution is defined on multi-dimensional simplex. This triangle and then later like multi-dimensional facet is called simplex, and it guarantees that any point that you pick in the Dirichlet space, when you decompose it into the components, they are valid values for those parameters because they all sum to 1. for the probability. Basically, a nice distribution on the multi-category variables. Okay, now what? Now let's do a little practice, and let's just give you a bonus by solving your homework problem. And our homework problem was about fruits in boxes. Those are kind of baby steps, but I think you need to internalize that, and we will use this just in a moment in the next slides. That's why I'm following that with you. And also, of course, I want to be able to claim that I showed you how to solve homeworks problems, but really, it's homeworks problems is your responsibility. You need to spend time thinking about them together and discussing them so you better understand the material in the lectures. So the problem 7 from homeworks, we're given 3 colored boxes. Well, the number can change, but we're given 3 colored boxes with the following fruit content. R is the red box. Red box has 3 apples, 2 oranges, 3 limes. G is the green box, has 2 apples, 4 oranges, and 1 lime. B is the blue box, 2 apples, 1 orange, and 0 limes. What is the probability? Oh no, actually probability of picking each box is given to you as well. So probability of picking a green box, probability of picking green is 0.2. Probability of picking red box is 0.2. And probability of picking blue box is 0.6. And the question is that we will address now as an exercise. A box was selected at random according to above. Just above is on the side in our slide. And a fruit was uniformly randomly picked out of it, and it turned out to be an orange. So what is the probability the fruit came out of the box? That's where the reverse conditioning rule comes through, right? That's important. So we know there's 3 values, and we know also probability of an orange given a green box, right? And the probability of an orange will be 4 out of 7. I believe 4 oranges, 2 apples, and 1 lime. Yeah, and what else do we need to solve the problem? I think we've got everything. So the question is, a box was picked at random, yeah, and what is the probability that it's green box if we know that we are looking at an orange? What is the probability of this orange coming of a green out of a green box? How to solve that? Well, probability of orange given green box, probability of green box, and probability of an orange. So that means probability of an orange given a box with marginalizing or summing over all of the values of B, right? Of the box. So that would be, well, B belongs to 3 boxes, red, green, blue, box. Let's call it X box. And we can easily solve it with all of the information that's available. At least for the top part here, we know already this is 4/7, and probability of green box is 0.2. And for the bottom, you just compute probability of an orange given green times green. which we have on top. And then we also compute probability of an orange given red times red. That's fairly easy, right? And for the orange coming out of a red box, it's 1/4 times 0.2, and probability of an orange coming from a blue box times probability of a blue box. That's all easy. That's 1/3, 0.6. So, and after we sum all of that up, we get probability of an orange, marginal probability of extracting an orange with this kind of a random process. And if you follow through with calculations, which I done myself separately, you get about 3.14 approximately. That's your homework problem part A. And then you can solve for part B easily yourself. Now, this probability, Bayesian probability problems, because they're useful in our next section. Imagine we have an AIDS test. And for AIDS test, we know that approximately 0.1% of the population of people are infected. And then the test that we have, the test is pretty good. It's super good. It detects all infections, no false negative. If there is an infection, it will be detected. And the test reports positive for 1% of healthy, sorry. So it can detect incorrectly, so it can have false alarm. So false positive in 1% of the cases. So I'm writing for you that we are using Bayesian rule, reverse conditioning, probability of the test of being positive given the person have AIDS times the prior times the evidence, and that's how we get posterior. And our evidence is nothing but joint marginalized over all possible values of AIDS, and there are only two, yes or no. And in this case, the test gave a positive result. What shall we do? How shall we proceed? Okay, probability of AIDS, let's put a numerical value, is 0.1%. Probability of not having AIDS then is a complement, is 999 ten thousandths or thousands. Then probability of having of the test coming back positives given the AIDS is 1. The test never makes a mistake of false negatives. But now probability of test giving us a positive when the AIDS is not there is 1%, 0.01. So we've got everything. If we follow through with computation, we will see that actually if the test returns a positive result, the actual chance of having AIDS is only 9%. Look, this is the best test ever. It detects all AIDS when it's present. It doesn't miss it. Why is so low? So we need to go back to the lab and spend billions of dollars on another test, or can we do something something interesting that is not as expensive and yet useful? Turns out, yes. Imagine that we have another test. We can use another test, a follow-up test, for example. And this test too is not as good. It reports positive for 90% of infected, so it misses 10%. So 10% of false negative. But it also is worse in the other respect. It reports positive for 5% of healthy people. Remember, the first test was super good, no false negatives, and only 1% of false positives. This one is quite an inferior test. But let's try to use it together with the first one, or rather independently, but on the same person. So in order to compute probability of having AIDS, if both of those tests give us positive result, we would need to use Bayesian formula again and Bayesian theorem again, Bayes theorem. Likelihood of those tests turning up positives when when the person is really having AIDS prior, and our evidence marginalize out all the values of AIDS and just get the test. So the trick here is, well, just let's look at this. We tested positively. What we're going to do? Well, we know a couple of values. We know that probability of having AIDS is a tenth of a percent, and not having AIDS is 999 thousandths of 99.9 percent. Then we need to compute the probability of both tests turning positive given AIDS. But what we know, those tests don't depend on each other. They are dependent on like the outcome, the value, of course, depends on presence of AIDS, but they don't depend on each other. That means, as before, that our test one joint conditional distribution is product is this product. The tests are conditionally independent given the outcome. So we can easily compute this value because we know the first one, the probability of test turning positive given AIDS is 1, and the second test probability of test turning positive given AIDS is 0.9. So this value is 0.9. And then the second, then the next part is probability of both tests turning positive when there is no AIDS is also conditionally independent, right? It's also, well, the conditionally independent variables. So we can use the same factorization. So probability of first test turning positive when there is no AIDS is 1%, right? So it is 0.1. And probability of second test turning positive when there is no AIDS is 0.05, 5%, which is, yeah, that's painful. Okay, so we got it and can move on. And to move on, we've got everything that we need. We can compute the marginal, and we can compute we can compute our likelihood times posterior. So I've done the calculation for you and got probability of AIDS if both tests turned to be positive is 64%. Amazing, right? So if we use only one test, super good, perfect, like almost perfect, just 1% of error. The posterior of having a test, if this test is positive, is only 9%. But if we use two tests, each of them is non-perfect and one is worse than another, but we still increase our confidence, we increase our detectability, so to say, of the disease by a lot, like almost 10 times, well, slightly less than 10 times. So in this case, our outcomes are not dependent, but test one and test two, like the outcomes are not independent, right? If one test is likely to be positive, the other one is likely to be positive too. But uh, like there is a conditional dependence of those two tests. So here's a $1 million question. Why not to use the same test twice? Think about it.